know is important now for the functioning of the ecosystem. And part of this has to do with maintaining disturbances. So floodplain rivers and rivers that I've been talking about today have all this complexity in them because they're continuously disturbed. Things like floods rip through them, and here's a little stream that used to flow out over here. Big storm came through and it blew out, took a new path. If this was Washington, the Department of Transportation would be out there with their bulldozers trying to put their stream back in its channel. But this is what streams do. They wander around across the floodplain in response to disturbances such as floods. And it's this type of erosion pattern that produces this mosaic of habitat that salmon need to thrive under. And just to quote Aldo Leopold, who I'm sure many of you know is one of the godfathers of conservation in the US, he said that to keeping every cog in the wheel is a first precaution of intelligent tinkering, describing how we need to maintain habitats and keep biodiversity around. He was probably thinking about this because he did think about so many things, but I guess what I think we should add to this is we need to think about what the processes are that produce the diversity in the first place. And in the case of salmon ecosystems, they're typically highly disturbed sites. They've been disturbed by glaciers, and they're continuously disturbed by flooding events and erosional patterns. And that's what produces the spice of life that makes these salmon ecosystems resilient. So if we go to the lower 48, this is the Skagit River. It's a big river just north of Seattle. This is our best estimate of what the wetland complex looked like in the 1860s. Lots of color here, lots of different small tributaries, large rivers, etc. And then mostly Dutch guys showed up and turned this into a big tulip farm. And what they did here is they drained and diked this whole thing. And what they did was simplify the system and take all these options off the table that would be used by fish, and presumably were used by fish in the 1860s. Now there are tens of millions of dollars being poured into the Skagit River to try to get some of it back. And despite a lot of effort and a lot of money and a lot of good people working on this, it is really expensive and incredibly ineffective. They will never be able to get the system back to where it was unless they buy up all that farmland and take all those dikes out, etc. So the message here is, thinking forward from this stage, we can actually do a lot to protect the diversity in the system and therefore the resilience in the system. And these sort of things are coming to Alaska. I mean, you can see it here in your backyard. Here's a beautiful image that Chris Stark from UAF lent to me. The Chena River up near Fairbanks, here's the main channel wiggling through the floodplain here. But all of these things are old relic channels that were left behind as the river migrated across the floodplain. Well, these are partially connected and seasonally connected, and you can guarantee that these backwaters were used as critical habitat by juvenile salmon and other juvenile fishes. Well, now we have a highway rolling through here, and I'm sure there's some good culverts and whatnot along this, but what we've done is basically constrain the river here so that it has limited capacity to wander across there and keep generating that habitat, which you can guarantee is critical for maintaining the productivity for the fisheries. And there's some really good examples of land trusts in Alaska that are doing their best to try to conserve land. The Tim Troll and gang with the Bristol Bay Heritage Land Trust are making a lot of important successes in places like the Nushagak to try to protect places of habitat that are important to fish. And again, part of the message here is it's easy to get sucked into thinking about we need to keep the main stem rivers, the big chunks of habitat. But what we now realize from studying these systems for decades is that all those little small pieces also matter a lot too. So what you need to think about when you think about protection for fish is you need to think about that network of habitat that fish use, both over the course of a single life cycle, but over the course of a single life cycle as it plays out over decades or even centuries, if you want to think that far into the future. So really the message here is that stability and productivity of fishery systems ultimately derives from diverse and changing habitat. Nature doesn't exist in a single static condition. It's a complex system, and the system is this moving target. And that's the type of system that salmon have evolved to, And that's the type of system we should aim to maintain if we want to keep productive fisheries in the game into the future. So thanks, I'm happy to answer any questions.
And if you have questions, please use the microphone so that we can conserve your questions for the radio. Questions? It's scary.
Yeah, on one of the early slides you had on there, it showed, you were showing how the composition of the total Bristol Bay run was changing over time. And reaching way back to the early 1900s, were they monitoring all those streams even though they weren't producing streams? How did they get the stock compositions back then?
So what I showed you was starting in, I think, 58 or 62 was the first year. So UW people did some stream surveys in the 1940s, and that's what we've continued through to now. Prior to that, no one was doing anything on the spawning grounds.
Thanks.
Well, the canneries were actually, they had these, what were they called? Cannery, anyhow, not superintendents, but they'd be out there looking at the quality of the product, etc. But some of those folks were actually interested in the biology, so they'd be out hiking around trying to estimate where the fish were going and these sort of things. But getting around that part of Alaska in the early 1900s was pretty tough going, so they didn't see a lot of the landscape. After World War II, there were planes everywhere. That's when the biologists really could get around the landscape really easily, and that's when some of these ideas were starting to be appreciated. And of course, there's traditional knowledge too that talks about where the fish were historically. But again, the traditional knowledge was mostly focused on the bigger tributaries, not necessarily the finer scale things that we actually go out of our way to study because we're paid to study and we don't have to go there to catch fish to make a living on it.
I guess another question if no one else has one, but when you mentioned, I think it was the White Act, was that when the game plan was to let half the fish escape and then catch the other half?
Yeah.
I remember I worked at Cardiff for a while, and I think the way that they did it back then was they tried to harvest the first half and let the second half escape.
Yeah.
And they get a real change in the stock composition. Was it like that in Bristol Bay as well?
The Bristol Bay management system is remarkable in a bunch of ways because a lot of these ideas about diversity have been appreciated by those managers for decades. So what they have is they have an escapement goal for the season, but then they also have a schedule of escapement basically by day over the course of the season. And the managers are all motivated to try to distribute as much of the harvest over the entire run as much as they can. In practice, yeah, they load up a little more harvest on the back end than on the front end. But in general, I think they do a very good job at trying to allow as much representation across the entire run to escape into the watersheds.
So that was a strategy even back when the White Act was in place?
Not during the White Act. The White Act was just they have an escapement goal, sort of. I'm not sure they really had anyone to enforce it, and they just hammered them after that number had passed up the river. It's more though, since Fish and Game took over, that they've been trying to distribute the harvest over the course of the run. And new genetic techniques and better monitoring, these sort of things have made them even more effective than they were, say, 40, 50 years ago. But again, it's in terms of Fish and Game, they've sort of appreciated a lot of these ideas, trying to fill up the spawning grounds is the way they talk about it.
Okay, excellent presentation, thank you.
I can only get questions from the scientists in the audience.
So Daniel, your presentation suggests that there is some caution that should be taken if we define critical habitat based on a study done one year, that maybe the critical habitat the next year might actually be a little bit different, and that the lateral habitat is really important, especially in high flood years. So when we think about conservation priorities, what's your recommendation for how, at a regional scale, we think about protecting important habitat for fish?
Yeah, it's a great question. I think the simple message is that if you go out and you sample where the fish are in any given year, or even a small number of years, you're going to estimate a much smaller proportion of the landscape that they actually use over longer periods of time. And over the course of decades, fish will use some pieces of habitat that you would simply write off as unacceptable or unviable habitat in some years that become important, say, during those flood years, or become important because they're a cold water refuge during really warm years. So the message is really, think about how to maintain habitat options for fish over long time periods. And really what that means is protecting the floodplains, protecting the riparian areas along floodplains, and allow rivers to wander around in those habitats to generate this fine-scale habitat, off-channel habitat. Some's cold, some's warm, some's productive, some's unproductive. It's that mosaic that matters. And what you need to protect are those areas around the active channel. Again, we tend to focus on, here's the water flowing through the river right now, that's the important stuff. But the reality is, if the river is working the way it should, a few decades later, the river may actually be over here, and that remnant channel is what is used by baby fish to stay warm or get away from predators or whatever. So ultimately, it's about protecting the floodplain, allowing the rivers to wander around, and create the habitat that fish use.
Sort of related to that question, doesn't it scare you a little bit at the scale of climate change? When you looked at your very first map of the red spots on the world might be a little bit too large to factor in when you look at a river channel compared to the scale of climate change. And that's what really strikes me with your presentation is biodiversity is really important, but we have this enormous, elephant in the room of temperature change that's going to affect everything.
That's true. You look at the scale of global climate change, and it is scary. I mean, the models that were the most extreme 10 years ago and were written off as liberal-minded academics who are out of touch with reality, we now realize that those model projections for the trajectory of climate change were actually conservative. We're beating them. So part of my message here today is we're going to have to do some things to deal with climate change. Reducing emissions is certainly part of the action, but maintaining habitat is something we can do now in real places, because it's the real places, it's places like this river valley that is going to affect people. It's not the global average that's going to affect people, it's how the climate plays out in certain places. In the case of fish are not encountering that climate directly. The fish are encountering the climate as it's filtered through the local habitat conditions. The hydrology, the topography of the ground that it's flowing over, interactions with groundwater. So you think about what we can do to deal with climate change, we can protect habitat at local scales, because that's tangible and it's going to have real effects, I can guarantee it. Where the tipping point is, it's out there in the future somewhere. I'm not sure we can really predict that. But if we want to be at least a bit optimistic, protecting habitat is something we can do that will have tangible benefits.
So Bristol Bay is an amazing exception, and what we deal with in Cook Inlet and other areas throughout Alaska are trying as hard as we can to protect the habitat inland and recognizing what's going on there, be it mega projects or roads or whatever, and water temperature. But that seems to only be half of the problem. The other half seems to be out there in the ocean somewhere. And any insight into that? Like, it seems like as hard as we try inland, we still have this other uncontrollable beast out there that isn't always acknowledged.
Yeah. So yeah, the ocean is a big gorilla that has its own behavior, and there's not much we can do about that. We can have effective fishery management that's mostly playing out in the marine part of their life cycle. But the other way to think about it is the ocean is going to send different numbers of fish back to watersheds. And during certain years, the ocean is going to be a very productive place, and it's going to send lots of fish back. Here we can use experience from places like Oregon, where during the 1940s, 50s, and 60s, the ocean off of Oregon was an incredibly productive place for coho salmon in particular. And what they were doing is logging the heck out of their watersheds And the more they logged, the more fish came back. And what they were doing was replacing freshwater habitat with hatcheries, okay? And because the ocean was such a productive place, the prevailing attitude at the time was, well, let's just keep pumping fish out of hatcheries. The ocean's gonna send them back as nice big juicy fish that we can catch. Well, then the climate changed, and the ocean off of Oregon headed south, literally, and was no longer a productive place to produce salmon. And at this point, all the freshwater habitat had been trashed, and they lost all their fisheries because the hatcheries could not produce the fish that were supporting these populations historically. So yeah, I mean, it's up to people like you who come out to talks like this to think about what do we want with our development projects. They are going to have effects, there's no question about that. So the question is, how much do we value some new mega project versus the habitat that produces things like fish that do also have tangible economic and social values. In some cases, they may be totally compatible. In other cases, we can't even pretend they're going to be compatible because they're not.
I have a question about the genetic diversity over small areas, small stream segments that you mentioned. Our local stream, the closest one here, just 3 miles away, has got probably the largest escapement for the entire Matanuska, just a short little side tributary. It has a unique stressor, the outflow for the city of Palmer sewer system. And interestingly, they seem to be linked. The question is, how long did it take is there genetic diversity likely that enables them to adjust to those particular unique habitats, which includes obviously a very high nutrient and food source?
Yeah. Yeah, so really the question, I think, is how quickly can salmon evolve new genetically based strategies to changes in the environment? And the best example of this is from some of Tom Quinn's work, who's another professor at Washington, who went to New Zealand to study Pacific salmon. And New Zealand, of course, didn't have Pacific salmon down there, but in, I think, around 1910, they transplanted a single population of salmon from the Sacramento River, and they moved it into, I think it was 7 or 8 major rivers in New Zealand. And these things established, they started migrating between the ocean and the freshwater. Who the heck knows how they figured it out, but they did. Well, Quinn went back in about 2000, so 90 years later, about 15 generations, and then went in and studied the genetics of each of the populations in New Zealand. Remember, these all came from a common stock. And within something like 90 years, each of those rivers now had its own locally adapted strain of Chinook salmon. They had their own timing of when they went to the ocean. They had their own timing of when they returned. The sizes of their eggs was different, and it reflected the local gravel conditions of each of those individual rivers. So the simple answer is it happens pretty quickly in ecological time. It can happen over the course of 5, 10 generations. And that's another answer here, is if we want to talk about resilience in the system, we have to let the system and the habitat evolve, but also give the animals a chance to evolve in response to the habitat. And in lots of cases, and we've learned this in the Pacific Northwest, is by flooding the system full of hatchery fish, we take away those evolutionary options for fish. So hatcheries we have to use really carefully if we don't want to screw it all up in terms of the evolutionary potential of salmon.
I was just wondering if you experienced any straying of salmon from more favorable habitats, if you knew what stream or watershed they were going to come up to through the isotopes dropping in.
Yeah, that's a good question. The question about straying, and this is one of the paradoxes of salmon biology, because we all know that salmon come back to spawn in the place they were born. But at the same time, we know that if, for instance, if a glacier recedes as it is in Glacier Bay and a new stream is formed, there's fish that find that place within a couple years and start establishing there. So this is one of the remarkable things that salmon do, is they have high abilities to go home to their home stream, but they also are really good pioneers. They can find new habitat when it becomes available. And as scientists, I don't think we really know what allows them to both be good prospectors, but also show high fidelity to their home stream. The simple answer is we know that fish do stray into new habitat all the time. And some of that's adaptive. I mean, you think about being successful in a highly disturbed landscape like after glaciers have receded, and the adaptation is to be weedy and colonize all the new habitat. Salmon do that really well. But they also have this ability to go home to their natal stream. That's a paradox that scientists don't have a really good handle on how it works out. We do know from genetic studies in places like Bristol Bay that do have lots of salmon in them, is that if a salmon comes back to a stream where it wasn't born, it's very unlikely to be successful at finding a mate there. Whereas if that same fish goes back and spawns in the stream where it was born, it's much more likely to be successful in its home stream. So it has something to do with this habitat being open that makes it successful. But it's a big mystery still. It's a great question.
I guess you showed that one slide earlier where you added, had to do with the ice breakup, and you added 2016 on there, showing very early. I assume there were really warm water temperatures going on there too. Were you seeing an increased incidence of just salmon that were dying from heat, just from thermal stress?
So that's what's interesting here. Last year was unbelievably warm. The water temperatures were warm. The fish looked amazing. The fish looked amazing. They figured it out. They found cold water refugia either deep in the lakes or they pool up off of cool streams coming in off of steep watersheds. And we saw very little pre-spawning mortality.
And were water levels okay, that they weren't getting stranded from streams, petering out or something?
No, I mean, the water levels were definitely low. There was low snowpack, and streams that depend on snowmelt were relatively low. But again, these fish, you've seen this, they can wiggle through really tiny amounts of water. And one of their biggest, at least in the small streams, avoiding the predators is one of their biggest challenges. But then they sneak in at night. We have fish that move into these little tiny streams. They sneak in at night, they spawn, and they get out of there before they get nailed by a bear. They have these, this remarkable portfolio of behavioral strategies for dealing with all sorts of warm and cold conditions.
I've seen them on the good news drainage where the outlets of the streams dried up and the fish couldn't get up into the lake itself.
Yeah.
And they ended up just stalling out and dying right in place.
So that certainly occurs in some places at some times, but then, I don't need to tell this to you, but for each one of these female sockeye that drops her eggs in the gravel, those eggs will spend most of a year incubating in the gravel. Then they'll spend 1 or 2 years in the lakes before they go to the ocean. And then they'll come back after either 1 year, 2 years, or 3 years in the ocean. So then you think about why would evolution do that? Shouldn't evolution produce the optimal behavioral strategy? Well, your optimal behavioral strategy is for that female to have eggs that do a whole bunch of different things. Because if there's a bad year like the one you're describing now, well, the fish that return next year from that same mom are more likely to make it successfully next year. So they're hedging their bets against uncertain climate conditions. And with climate change, we may see lower water levels and more stranding that's going on. But right now, it doesn't, it hasn't played out to the point where, we've been concerned about it.
I wondered if you had any comments on your component analysis where you looked at the depletion of marine nitrogen, I think if I understood it, over the last 100 years, if that has any consequences for ecosystem in the lakes.
Yeah, so that's been on a lot of people's minds about the idea that commercial fisheries are intercepting all these marine nutrients that are coming back to watersheds. And we've put a lot of effort into trying to understand this one. And here's my simple answer for you. There's certainly less marine-derived nutrients coming back to these lakes now and these watersheds now than there was before commercial fishing. It's probably on the order of a half to a third as much as coming back now. We can also show you from the sediments that there's less algae in those lakes than there was in the 1800s, okay? But if you look at how many fish are produced from these lakes, and this is the escapement plus the catch, there's just as many fish, or even we think a few more fish produced now than there were before commercial fisheries developed. So the ecosystem, if you're interested in the growth of algae, is probably less productive now than it was historically, but the systems are producing just as many fish. What this tells us is that what's limiting in these watersheds is probably not the nutrients, but the amount of spawning habitat. I think places, or the components of the ecosystem that are most likely to be affected are the direct consumers of salmon. Things like bears, things like trout, things like birds. But again, looking at our systems here, they're not constrained by the number of fish that return, they're actually constrained by the duration of time they have access to salmon, which is really a reflection of the life history diversity in the watershed. And as best as we can tell, there's been no erosion of the life history diversity in these watersheds, and that they still have this long access to salmon. So you also hear crazy stories, particularly in British Columbia and lower 48, that salmon runs made trees grow big and these sort of things. And that's bordering on ridiculous. You just add up the nutrients brought back by salmon, it doesn't add up to enough to make a difference to trees. So it's a bit of a mixed bag, but you know, I believe that salmon are important in these watersheds, but I think what they're most important for are the animals that eat them directly. The fertilization effects, the evidence for that is very, very weak. It's a great story. It's a story of biblical proportions, but it doesn't hold up to the data.
What about over-escapement?
Over-escapement, are you a fisherman?
Sport.
Sport fisherman, okay. So over-escapement is this idea, for those who don't know, maybe everyone knows this, the idea is that if the, it's mostly propagated by or promoted by commercial fishermen, but the idea is if too many fish are in the watersheds, that competition amongst those fish is so intense that very few of them return. So the idea is you have to harvest them relatively heavily to make sure that not too many fish end up in the watersheds. Well, again, if we ask the data to question whether there's support for that over-escapement issue, and it's essentially non-existent. For Chinook salmon, there's some evidence for it in some rivers. For sockeye salmon, for pink salmon, the evidence is very, very shaky. The whole idea of over-escapement is a bogus idea in my view, from an ecological standpoint. From an economic standpoint, clearly over-escapement is a reality because those are fish that could have been harvested that aren't necessarily contributing to the population.
Thank you.
Yeah, thanks for the presentation, it's great. One slide you showed the returns to the Keyjack, I think in the 50s and 60s were really high and the other rivers were not contributing. Any speculation what was going on there?
Yeah, well, scientists can always speculate, right? So how long
we got time.
Yeah, you know, so the simple answer is we don't have a good understanding for why these things shuffle around. For the Keyjack, we do know that a lot of the fish that produce those monstrous runs were fish that spawned on some of the islands, which is a very unique, eco-type of salmon. And what I think is going on is that for random chance or whatever flukes of nature there was a couple generations of salmon that did really well on those beaches in Iliamna Lake. And then they sort of resonated for a few decades and went away. Why the other rivers came back up, that was coincident with that. A lot of it happened in the mid-70s when there was a big shift in the Pacific Decadal Oscillation. And rivers like the Wood River became substantially warmer. And when those lakes warm up a little bit, they produce better growing conditions for the juvenile sockeye. They grow a little bigger, they probably survive a little more when they go to the ocean, and their productivity came up. The Keyjack, you know, Iliamna is such a big lake, it really didn't warm up very much after the 70s, so I'm not sure that there was much of an effect on the growing conditions. But I'm just telling stories. We don't really have a good explanation for what caused this shift. We just know it happened. And the fact that it happened tells us something about what are some of the important attributes of these ecosystems, and that's this complexity. Was there another question here?
I was just wondering if you saw any correlation to, like, I guess you could call it overescapement or overpopulation of a river and lower oxygen availability and productivity of eggs.
Yeah, that's a really good idea too, that if you get, this is a mechanism that could produce an overescapement effect. And that is true that when you get a high number of fish in the streams, they do consume more of the oxygen, and therefore they could die. So there are some rivers, the branch, or do you fish in Bristol Bay?
No,
No.
I fished in Western Alaska.
Okay. So the Lagnac River a few years ago had some monstrous escapements. They had escapements of 5 or 6 million fish into these relatively small rivers, and they had massive pre-spawning mortality events. And those occurred during some really hot conditions when the water temperatures were warm, and probably there were so many fish in there that they were also stressed by oxygen. In most of the systems we work in, we don't see oxygen stress. They're shallow enough that the oxygen is exchanging with the atmosphere, and the fish seem pretty tolerant. In the case of coho salmon, coho have pretty unique, or silver salmon, they have pretty unique physiology, so they can actually tolerate really low oxygen conditions. And that's one of the reasons they're really successful in beaver ponds and wetlands and these sort of things, is they can handle those low oxygen conditions. So yeah, that process probably does play out in certain places and times, but I don't think it's very common.
Thank you very much. I'm just supposed to wrap this up, and I don't have much to say, but just to bring it back to the Mat-Su, I mean, there's a lot of talk about, is it important to protect Cottonwood Creek, or Wasilla Creek that's in the middle of, our cities and our subject to urban development. And as Daniel was talking, Dr. Schindler was talking, I was thinking, yes, I mean, that's one argument for protecting these streams, because you could say, well, what's Cottonwood Creek? It's not important. We've got the whole Deschka River, we've got Cashwitna, we've got all these streams that are totally unimpacted. So why worry about this impacted stream, in the middle of our town? But those streams, like Cottonwood Creek, may be super important if a time like 2012, where we have a flood event, the little Sioux's washing out, the Cottonwood Creek that has this lake system that ameliorates the flows, that may provide kind of refuge during those disturbance events in other systems that provide the resiliency to the overall system. So a good argument for protecting our urban streams, our impacted streams, and even your own property along those streams. I'd also like to encourage any of you that aren't members of the Mat-Su Salmon Partnership to look us up online, and there's this handout on the table back there. It shows a little bit about what the partnership's doing, and then also feel free, of course, to come and listen to the talks tomorrow. Thanks again for coming tonight. Thanks again, Dr. Schindler.